is, well, it's actually quite similar to some of the stuff Radu was talking about. Classical observables from amplitudes. So there's a couple of reasons to think about this. Of course, one of the reasons is that a classical observable you might be interested in is the gravitational waveform. And that's something I'll talk about, not today, but in my next lecture. Obviously, the gravitational waveform is a pretty interesting observable. But more generally, it's interesting just to wonder what kind of observables can we compute with scattering amplitudes. The topic of my lectures is the double copy. The double copy, it's a very interesting point of view on gravity. So there's a question then of, can I compute some particular observable that you might be interested in using the double copy, right? Well, the answer would be yes, if I can convert that observable into an expression in terms of scattering amplitudes. It's also just sort of interesting to, spend some time puzzling about what sort of, what are the space of observables that are directly connected to amplitudes. Okay, so the basic idea that I'm going to follow, it's a bit different from Radu's discussion. The basic idea here is to, first of all, pick an observable that you might be interested in. So pick an observable. Now, it should be an observable that makes sense. That is to say, it should make sense both in the classical theory and in the quantum theory. I mean, obviously, if I'm interested in classical observables, I don't want to have an observable which counts the number of photons in a laser beam, right? Perfectly observable thing, but it doesn't have a classical meaning. So I'm going to restrict to observables which are, pick an observable which makes sense. Both classically and quantum mechanically. Of course, if it doesn't make sense quantum mechanically, I'm going to be in trouble connecting it to amplitudes, classically and quantum mechanically. And secondly, we have to pick an initial state that we're going to be interested in. Pick a sensible initial state. I'll spend a while talking about this. So a key point about this initial state is, well, I have to talk about states if I'm doing quantum mechanics. But if I want to do, if I want to extract expressions for an observable that makes sense classically, well, then my initial state better be, have some sensible interpretation classically as well. And then 3, so the final state. So let me say my initial state is psi. So the final state will be obtained by acting with the time evolution operator on psi. So if I go from asymptotically far in the past to asymptotically far in the future, the time evolution operator is the S matrix, as Radu said. Now this is the full S matrix. I'm not going to work in any 2-to-2 situation, the full S matrix. But that's the final state, so I can then use this final state to compute expectation values of observables in the far future. Right? It's expectation values that make sense in the quantum field theory. Okay, so that's the basic program. Okay, so today I'm going to focus on a particular observable. And I'll talk about other ones in another day. Today focus on the impulse. Try and spell that. So the impulse, which is the total change in momentum of a particle during a scattering event. Right? So I'll take 2 particles, scatter them, and compute the impulse. So classically, the impulse is just delta p integral over all times, minus infinity to infinity, d tau, dp mu d tau. So just the total change of, say 1 particle, let's say particle 1. Okay, so perfectly reasonable observable classically. Quantum mechanically, I can compute the expectation value compute the expectation value of a momentum operator. That's a reasonable thing. So P1 mu. I'll try and give my, well, yeah, I will fail, but I will give many of my operators this sort of blackboard bold font. So that's a perfectly reasonable operator in a quantum field theory, right? You know, always going to have a momentum operator. Okay, now I can compute this expectation value in both the far past and the far future, right? So in the far past, the expectation value will be just psi, my initial state, P1 mu, psi. In the future, I can compute psi S dagger, P1 mu S psi, right? So S psi is my out state. So this is going to be the expectation value of the momentum of my particle in the far future, and the impulse will be just the difference. Delta P mu equals psi S dagger P1 mu S psi minus psi, and then I'm cunningly going to leave a little bit of space here, P1 mu psi. Now, one way to simplify this is just to introduce unity here in the form S dagger S. So this thing becomes, well, it sort of looks like a commutator. Commutator of P1 mu and S on psi. Okay, so that's a basic expression for the observable. Now, it's usually convenient to write S is 1 plus IT, right, to introduce the transition matrix. One plus IT, so that this impulse becomes delta P mu. Yeah, so now there's one term. So let's see. So the unity in that commutator is going to cancel away. So I can always replace this S with I times T. So one term will have IT, and the unity from the other S matrix, P1 mu. And the other term then is just going to have two T's. Psi, T dagger, commutator of P1 mu and T, and psi. It would be 0 if I looked at the total momentum, but here I'm just looking at the momentum of particle 1. So this should be momentum operator particle 1, momentum operator particle 1. So if I have several particles interacting, say, well, let's say 2, then you'd expect that the commutator of P1 mu plus P1 plus P2 would commute with the S matrix, right? The total momentum would commute with the S matrix. But this is just a partial one. Yeah, actually, you know, that's a useful thing to think about. For example, if I take two particles, let's say they're two charged particles interacting electromagnetically, then you really have three momentum operators in your theory. You know, the two particle momentum operators, and then the momentum operator of the entire electromagnetic field. So the sum of all of those is going to be conserved. But you can certainly dump some of the mechanical momentum, like the momentum of particles 1 and 2, into radiation. But you're guaranteed from the start that total momentum will be conserved, which is, you know, in some ways a nice, well, I mean, you're doing quantum field theory, your conservation laws are reliable. It can be confusing sometimes classically when there's, you know, when you're dealing with radiation reaction. There's never any problem here. Okay, very good. So now, a first observation, I'll maybe add more detail on this in the middle in a minute, but you know, this term here has got one T, right? T is the matrix of amplitudes. So there's a term here that's going to have one amplitude. Here there's two T's. Again, you know, that's two matrix elements of amplitude, so there's going to be a term with two amplitudes. And that's it, right? This is all orders. I didn't make any perturbative approximations. Okay, of course, more generally, there was nothing particularly special about the momentum operator here. So the change in some operator O. So say delta O is going to be psi. Well, maybe just write it like this. Commutator of O, S, and psi. So I'm planning to talk about in the next lecture a case, where the observable really is the, say the Riemann curvature. So that will give us access to the waveform in some sort of scattering event. And then in my last lecture, I'm planning to perturb a bit further and use that as a basis for talking about exact solutions on the double copy. Any questions so far? Excellent. Okay, so it's important to think about the state. Now, if I'm working, well, let me say to begin with, I'm going to scatter two particles. Yeah, well, I'll scatter two particles. I want them to be massive particles. Two massive distinguishable particles. That's not fitting there. Two massive distinguishable particles. So particles 1 and 2. I'm going to, well, I will also consider charge scattering. If I'm doing Yang-Mills, they might have some charge. In gravity, it'll be enough that they just have some mass. And just to sort of set our expectations in gauge theory, you can think of the action should be roughly, essentially just the action for the Yang-Mills field, and then so some sum over particles, d mu phi dagger. Phi dagger, phi. These are all i's, and that sum, I guess, is over all those. Okay, so I'm not going to talk about an effective field theory like Radu had, right? So I'm sort of in the full theory in that sense. Good. So now, classically, you would set initial conditions. You'd have, give these two particles exact positions and exact momenta, and then let the dynamics take care of everything. Exact positions and momenta. Now, in quantum mechanics, I'm not going to be able to do that, right? I can't have both exact positions and momenta. So what I can instead do is have an initial state where the uncertainty in the position of the momentum is negligible. Uncertainty in position and momenta. Okay, so the picture, I mean, obviously the particles then have to be in some sort of wave packet. There's a wave packet that localizes them. So the picture for the particles will be, well, I'll take two particles. Well, let me draw a picture here. I'll put them in Gaussian-like wave packets. So then this would be particle 1, this is particle 2, separated by some large impact parameter b, with small little uncertainties in the wave packet. There could be different uncertainties in both wave packets. I don't really mind, right? But that uncertainty should be very small compared to the classical scale that I'm really going to care about, which is the impact parameter separating them. It's impact parameter b. So then the picture of the dynamics is, I'll take these two particles, separated by this impact parameter b, and shoot them at one another. Right? So they will scatter. Okay, so very good. So now, so we will have uncertainty in position. And I will call that this parameter LW. So some parameter that you feed into your choice of the wave packet. Now, by the magic of Fourier analysis, that leads to uncertainty in momentum. And we can, we know our Fourier analysis, so we know what the uncertainty in momentum is. It's just h bar over LW, so of that order, right? Now, these things better be negligible compared to classical scales of interest. Right? So the uncertainty in position better be very small compared to this impact parameter. The uncertainty in the momentum, well, that better be very small compared to the masses of these particles. Right? And this leads to a series of inequalities, which is useful. So notice that, well, let me define a measure of the Compton wavelength of the massive particle, h bar over LC. I could set h bar equal to 1, by the way. Radu set h bar equal to 1. Radu is a smart guy. Keeping the h bars in the problem is kind of a bit of a pain. So, and it's spectacularly likely that I'm going to mess up the powers of h bar here. So, please help me if you spot my h bars are totally wrong. That happens. Anyways, but I'm going to keep them because there's sort of an interesting point which I want to make later on about these h bars. They'll eventually disappear. Okay, anyways, so what do we learn? So from here, I learned that the Compton wavelength of the particle is very small compared to the size of the wave packet, and from here, that the size of the wave packet is very small compared to b. So, and this is the set of inequalities that's actually useful here. Yeah, it's sometimes handy to give these a name. They're sort of like Goldilocks conditions. So this is the set of conditions on the wave packet that guarantees that the classical, you sort of got a sensible classical initial situation. Okie dokie. Very good. Now, more generally, so this impact parameter here is b, but when the particles interact, they don't always stay a distance b apart. Right? So more generally, what you really want is that for the classical dynamics to be reliable, the classical approximation to the quantum field theory to be reliable, you need that the particles are always, for their separation throughout the entire dynamics should satisfy this inequality. So let me say that the momenta of the mediators, whatever's mediating the dynamics, could be gluons or photons or gravitons, say that the momenta of these mediators are Q. Well, Q is going to be of order h bar over b. I mean, more generally, I mean, if the scattering is quite strong, this might be violated, but there will be some scale here. Let me say, a better way of thinking about this really is that there's some scattering length. So this is sort of the closest distance between the particles throughout. So then these momenta will be roughly of order of that. Rather than b here, I'd have this ls. Maybe I'll write ls here. So this is sort of the typical momenta of these mediators. Now, excellent. So that means that LC, this Compton wavelength, is small compared to LW, which is small compared to h bar over this ls. Yeah, there you go. So another way of thinking about this is that ls is of order h bar over q. And well, that's totally messed up. That's an ls. You're supposed to help me. Okay, so now I want to just come back to a point that Radu was making in a previous lecture, sort of relating these q's to the mass of the particle. So if ls, since ls is of order h bar over q, And this Compton wavelength is order h bar over m. We have h bar over m is very small compared to h bar over q. So in other words, q is very small compared to m. So the momenta in these, the momenta in the mediators is small compared to the mass of the particles. Okay, so this is the the set of inequalities that we need to arrange for the dynamics to maintain us in the classical approximation. That's the basic idea here. Now, excellent. So just a couple of comments here. Maybe I should move over here. Just a couple small details. So first, I'm going to ignore finite size correction. So I'm thinking of really pointless structureless particles. So that might be relevant because, maybe you want to consider scattering black holes or something like that. Black holes have certain finite size effects. I'm ignoring those, just to keep my life simple. We could include them if we want using, by adding some higher dimension operators to these theories, for example. I'm not going to do that right now. Another thing that you could imagine doing for these finite size corrections is building them somehow into the wave packets. Maybe you take that size of the wave packet as being, really a scale of interest in the problem. So you have a blob with some size LW, and you consider the scattering of that blob, like it's a finite size blob now. You could do that, but I'm not going to consider that. So I'm always going to, that would involve mucking around with this, with these inequalities here. One way to think about them is that, one of these inequalities is arising from suppressing quantum effects, and one is arising from suppressing finite size effects. Okay, so no, not all. Yes, that's right. Yeah. I mean, more generally, if you wanted to put, you could put any finite size effect you want in the effective action. Yeah, that might be an interesting thing to figure out which you can put into a wave packet and which not. Yeah. Okay, second comment. Well, just on the physical interpretation of this. So in E and M, this is Coulomb scattering, which is pretty familiar. But if you work in the full quantum field theory, you're including radiation, right? So there's, so that's non-trivial dynamics, quite non-trivial. All of those effects of radiation reaction, Abraham-Lorentz-Dirac forces, etc., are going to be automatically included in GR. So the scattering is basically, classically speaking, the scattering is due to the non-trivial metric set up by these particles. So there's two particles. So that'll be, well, if you consider, if you work in post-Minkowskian theory, so expand in powers of G, lowest order, it'll be some sort of sum of the Schwarzschild metrics of these, of the lowest order Schwarzschild, but then there will be corrections, because of the interactions in GR. Okay, so that's the basic setup. All right, so yeah, some remarks on notation. So notation, yeah, I need some notation to keep the equations a little bit under control. So the state, so our state is some state psi. It's an integral. You want to integrate over, I'm going to work in momentum space, so I'm going to put the particles in momentum space wave packets. So then I'm going to have to integrate over those momenta. So there's going to be some integral over the momentum of particle 1, momentum of particle 2, a wave packet for particle 1, wave packet for particle 2. I'll insert the impact parameter like this, so a translation operator. I'm going to put a h bar there because I'm persisting in trying to keep the h bars. And then 2 plane wave states. Now, this integral is an integral over on-shell momenta. So integral is really over. So, well, you have to on-shell momentum of particle 1, there's a 2 pi cubed, there's a 2e of particle 1, and on-shell momentum particle 2, 2 pi cubed, 2e2. And I really don't want to write all of those 2 pi cubes. I don't want to write all these energies. So I'm going to introduce a notation here. I'm going to write d5 of p. So this is phi is supposed to be, indicate phase space. Right? So an integral over phase space. I'm going to write that as d hat 3p over 2e. So d hat p is a notation for hiding 2 pi's. And similarly, I'm going to have a delta hat of p, which is another notation for hiding a 2 pi. Right? The 2 pi is upstairs in the delta, downstairs in the integral. Now, this 1 over 2e, I can get that, make this look more Lorentz invariant, and that's convenient to rewrite this thing as an integral d4p with the delta function, delta hat, p squared minus m squared, and a theta function then of the energy, p0. Right. So these are the same measure. Okay, and then I'll write d5 of p1 and p2 to indicate these separate integrals, and I'll have d5s with more p's in them as well in a little while. Okay, so do ask if you don't understand the notation. I mean, it's just some funny notation we made up to try and keep our lives simple. So it's an excellent time to rub out that expression for the impulse. Maybe I'll try and keep part of it. Okay, so with that in mind, we can write what the impulse is in terms of amplitudes. Yep. Good. This? So this is e to the I b dot p1 over h bar. So its job is to translate particle 1 with respect to particle through an impact parameter b, right? Just to make up this picture here. Yeah, any other questions? Okay, so let's work out the impulse in terms of amplitudes. Okay, well, let me rewrite the expression, which I was partially erased here. Commutator of momentum operator 1, t psi plus psi t dagger p1 mu t psi. Okay. Yeah. Excellent. Okay, so I'm just going to write this out now in terms of this expression for psi. So excellent. So what I can do is, noting that I've got 2 psis, a psi and a bra and a ket, I really have an integral over 4 momenta. So I'll have an integral. So the d5s for the outgoing particles, put primes in those, and for the incoming particles. There's the wave packets. Now I'll write these 2 wave packets together. That's phi, p1, p2. The details of them aren't going to matter. So I have phi star, p1 prime, p2 prime, phi, p1, p2. There's an e to the ib, e to the ib dot p1 minus p1 prime over h bar, and then times. So outgoing states, p1 prime and p2 prime, I, the commutator, and then the t dagger term. Okay, excellent. So, so here are these two terms. Now, we can simplify them. The first term simplifies out quite easily. So the first term, so I mean the first term here in the integral, this first term, is, well, the momentum operator P1, well, acts first on the ket and brings out a P1 prime. And then it acts on the bra and brings out, that's the wrong way around, that's a bra and that's a ket. It first brings out a P1 prime and then subtracts off a P1. So you're going to get I times P1 prime minus P1 index mu. And then the matrix elements of just the T, right? So that's the amplitude, 4-point amplitude for P1, P2 goes to P1 prime, P2 prime. And then there's a momentum conserving delta function. Right, so that's just the first term, right? Okay, the second term. Well, there's a couple of ways of thinking about the second term. Now, one simple-minded way of thinking about it is just to introduce a sum over states in here, right? So that I split up that T dagger and this T. So you have to introduce a complete set of states. So you'll get, let me write an equation about this, P1, P2 prime, T dagger, P1 mu, T. Okay, so very good. So I'm going to introduce a complete set. Now, I'm going to assume that my particles 1 and 2 go through the scattering, right? These particles are supposed to be heavy particles. They're supposed to be distinguishable. I don't want them to decay in the middle of the process, right? So you could imagine that I'm, say an E and M or Yang-Mills, that I give these things some conserved number. I'm going to scatter them quite gently, right? I want my scattering to be gentle so that I'm, not going to be in a situation where my particles get too close and I start seeing quantum mechanical effects. So the way I tend to write this sum over states then is, let's say there's a sum over some particles x, but also an integral over the phase space of two intermediate particles of these types, 1 and 2. So P1, P2, prime, T dagger. So P tilde 1, P tilde 2, x. So x here can be any number of particles. The idea behind this x is that the particles that you can produce copiously are just, say in E and M, they're just photons, or in gravity they could be various gravitons, Yang-Mills gluons, right? I don't want to produce massive particles. That's not a classical process. Right? My Goldilocks conditions here are forcing my Q to be small compared to masses. So there isn't enough momentum here to generate new particles, right? So this sum on x is really just supposed to be a sum over a bunch of mediators. So I'm then continuing, x, P tilde 1, P tilde 2. And the commutator, P1 mu, T, P1, P2. By the way, so the x can also include the empty set, right? So there is a contribution here where there's just a 2 to 2 amplitude in this T dagger, and here another 2 to 2 amplitude. Okay. Okay, so the picture for the second term is that we have, well, let me say again. So once again, this commutator involving the P1 operator will pull out a factor. In this case, it'll be a P1 twiddle minus a P1, right? But some momentum type factor. And otherwise, you're going to get something which looks like this. So there's, well, let me write it like this. So particles P1 and P2 are incoming. I have So these twiddly guys in the middle. There could be a bunch of mediators in this state X, and then P1 prime, P2 prime. So, so from the first term, we got an amplitude. From the second term, we got something involving, two amplitude blobs connected together. This you can think of as being a cut of an amplitude. Right? So in both cases, both these terms just involve amplitudes, an amplitude and a cut of an amplitude. That's the basic idea here. They're always 2-to-2 amplitudes. Right? So just to return to a theme that people have been hammering at in this school so far, the nonlinearities in here. This Coulomb scattering process, like even in E&M, the Coulomb scattering is very complicated. It involves radiation of energy and momentum, involves radiation reaction. It's a highly nonlinear process. All of those nonlinearities have to come from the loop expansion of the amplitude. Right? That's the only place it can be, both of these. Very good. Okay, now I'm hoping that I'll manage to talk about some of the loop corrections to these processes in the next lecture, but for today, I'm going to focus on the tree level, the leading order. So then, so at leading order, I can forget about this correction, right? So you can sort of just power count couplings here. This is two amplitudes. This is second. So amplitudes involve perturbative factors. The tree level 4-point amplitude involves 2 powers of some coupling. So this will involve 4. So the leading order correction is entirely going to come from this first term. And I'll restrict to that first term for the rest of the lecture. Yes?
Hello. Okay. Yeah. Just if you could briefly repeat again the meaning of the X term there on the sum. What is it? What it is?
It's a bunch of mediator particles.
Just mediator particles. Okay.
Yeah. It can be so a bunch of gravitons, photons, gluons, things like that.
Okay. Depending on the theory. Okay.
Yeah.
Sure. Thanks.
Yeah. That's right. Yep. Another question.
Just to be sure, the particles like P1 and P2 tilde are off shell, right?
No, these are on shell.
Oh, on shell?
Yeah, they're on shell because they're associated with the state. States are always on shell. So once I put in this complete set, that's a state.
Okay.
Yeah, an on shell particle. Yeah.
Just to be sure, from those lines, that's a multiplication, right?
That's a multiplication.
Okay, so thank you.
Excellent.
What about bound states of P1, P2? Are they in X?
I'm sorry?
The bound states of P1, P2, are they in X?
Oh, bound states. Interesting. Yeah, bound states are an interesting question. So I'm restricting here to scattering states. I'm scattering these particles. Now, it would be very nice to talk about bound states. I don't know how to do that. If you do know how to do that, you could talk to me privately. It'd be fantastic. Or alternatively, write a paper on it. That would be even better. I mean, of course, inside in here, you are putting in a complete set, so there will, in principle, be bound states. But the parameters we're putting in are going to suppress them in this particular scattering type process. The particles aren't coming close enough to bind. Yeah. Okay. Excellent. Any other questions? Okay. Excellent. Okay, so let's, oh yes, there is another question. So photons, gluons, massless particles.
But no phi particles.
Hmm?
No.
None of these phi's. Yeah.
Yeah,
so I'm exactly.
Why?
So the reason why I'm not putting in any other phi's is because of this this relation here.
Okay.
I don't have enough momenta to pair produce new particles.
Okay. Thank you.
Yeah. The pair production is a quantum mechanical process. Not an uninteresting process, but to the extent that we're focusing on gravitation or classical observables, it's just something we can suppress. And it's suppressed by kinematics here.
only amplitudes that are non-zero, or for the ones that you're talking about?
That's exactly right. Yeah, yeah. So what Nima is pointing out is that this really is just a sum on everything. So the reason why you're not getting pair production of anything else, or the reason why it's just this sort of pattern of states, the two particles I put in are propagating through, and then a ton of potentially a ton of other massless particles, is by arrangement of the kinematic data, the initial kinematic data. Yeah, exactly. Okay, excellent. So at leading order, we have just the first term here, and my mission now is to simplify that into a form that we can easily use. Right? So delta p mu at LO is, well, from here, I probably will need more space. So it's this integral over 4 kinds of phase spaces. We have our wave packets, phi p1, p2. There's the exponential term here, so plus I dot b dot p1 minus p1 prime over h bar. And then there's a factor I, this factor I here, p1 prime minus p1 mu. There's 4-point amplitude, which I'll just call A4, and the momentum-conserving delta function. Okay, so to simplify this, well, one thing I can do is note I've got a delta function here. I also have integrals over these various particle momenta. Right? So let me do one of those integrals with the help of the delta function. So let's say I'm going to integrate over d4p2 prime with the help of that delta function. So use the delta function. P2 prime. So that's gone. So secondly, I will use it, I'll make a little change of variables. So think about my scattering like this. So P1, P2, coming out, P1 plus Q, so there's some momentum transfer Q there, and P2 minus Q, right? So what I'm going to do is change the variable in the integration over P1 prime to an integral over Q. So then the integral over P2 prime is gone. I'll just have a Q integral. So set P1 prime equal to P1 plus Q. So this is just a change of variable. Okay, so then this delta P will become, well, there will be an integral still over the phase space of particles 1 and 2, the initial P's, sorry, the initial P1 and P2. This phi star is going to be phi star of P1 plus Q, P2 minus Q, and then a phi of P1, P2. This exponential now just becomes e to the minus I b dot q over h bar. This thing is I q mu and the 4-point amplitude. Now, and I've left out the crucial thing, irritatingly. Sorry, let me write this again. So I left out the integral over d4q. So that's has its origin in this P1 prime integral. Now, there were also delta functions running around the place, which come from here, right? These were phase-space integrals. There's on-shell integrals, on-shell delta functions. So I better put those in too. So the on-shell condition on particle 1 outgoing is going to be 2p1.q plus q squared. Right? So p1 plus q squared must be m squared, but p1 squares to m squared already. So the p1 square cancels the m squared in this delta function. And similarly for particle 2, minus q squared. Theta, there's these theta functions over there as well. Theta p plus q0. So this is the condition that the outgoing energy of particle 1 must be positive. And similarly, the outgoing energy of particle 2 must be positive. Okay. And now I've got that exponential. b dot q over h bar, and then times I q mu 4-point amplitude. Okay, so it's not looking much better yet, right? But I can simplify it all relatively easily now. So firstly, well, let me note I've left out the phase space in the phi integrals. Maybe I should check this. Times phi p1, p2, iq mu a4. Okay. Okay, I think it's right. Excellent. So now, to simplify this, well, the physics I haven't put in yet is that I'm interested in a classical observable. Right? So all of this is just expansion of some state, some operators, and then a statement I'm going to work to lowest order in perturbation theory to get rid of this TT dagger term. But to simplify this, in the classical regime, I have to use these conditions here. Right? So now, one of the conditions, let me just use this one here. So the first terms in these delta functions are of order mass times q. Right? The second terms are of order q squared. So the second term is suppressed relative to the first term by a factor, q over m. So I'm just going to dump these terms. Right? Second simplification. The energy here in these outgoing messengers, again, is very small compared to the masses of these particles. So these theta functions are just unity because the initial configurations will have positive energies for these particles. So these things are just equal to 1, these two theta functions. Thirdly, this phi here depends on p1 plus q and p2 minus q. But the q is very small. So let's see. So the q is of order 1 over ls. So the correction to the wave packet here is very small because these wave packets in momentum space have this uncertainty. They're quite wide relative to the q. Right? So let me see. Sort of thinking I'm not being super clear on that one. So let's see. So this LC here is of order h bar over m. I don't really care about that one. The LW here is small compared to the LS, and the LS is h bar over q. So inverting this, the q over h bar is, let me see, this is, yeah. So I guess this is just the way I want to think about this. So the spread in size here is small compared to the size of the wave packet, so that I can neglect the q shifts here. So the net result is, let me come over here. So the net result of this is that the delta p is, well, I didn't touch this integral over phi. These wave packets now just become norm squared. And come out of this integral. And then we still have our q integral to do. It now is constrained by these two delta functions. There's this Fourier transform here. There's our IQ mu. and the 4-point amplitude. Okay, so now this, the role of these wave packets here is essentially quite simple at this point. Their only job in life really is to set the values of the P1s and P2s that appear in the rest of this formula. So we think of these things as steeply peaked. At classical momenta. Pi, which are mi times ui. So this ui is supposed to be some proper velocity of a classical particle. So to hide this integral, or well, to avoid to introduce another notation, right? I don't really want to run around everywhere in here saying the p's are really these mu's, right? So I'm just going to introduce a double angle bracket. And its job is just to say, well, when you've done the calculation, you set the p's to the classical values. Delta 2p2 dot q e to the minus I b dot q over h bar iq mu A4. And let's close our brackets. Okay, so again, those brackets just say, okay, you've done the calculation, great, now set p to be mass times proper velocity. Now, so this is the essentially classical formula. But there's one thing about this which, there's one way in which the quantum mechanics is still lingering. It's still, showing itself, and that's in the factor of h bar here, right? So, well, it's very easy to get rid of that. So, to do so, I'll just rescale the q. Right? So q here throughout has been a momentum. But I can introduce a new object, q over h bar, and give it a name, right? So from dimensional analysis, we know that q is momentum. H bar, which is an angular momentum, is mass times length. Momentum is mass. So q over h bar has dimensions of 1 over length. So I will set q over h bar equal, the notation we have for that is q bar. Dimensions 1 over length, it is a wave number. So it's the wave number of the modes in the interaction. Okay, so very good. So now if I perform this as a change of variable, so I'll integrate over q bar instead of q. Yeah, just a sec. Well, I'm going to get 4 powers of q bar, 4 powers of h bar from writing q. Q equals q bar h bar. So I'll get 4 powers of h bar upstairs, but minus 2 from the delta functions. They'll become delta functions involving q bar. And I'll get a third one from here. So there's something a bit funny, right? There's 3 powers of h bar. So delta p mu is, well, here's our double angle brackets, integral d4 q bar delta 2p1 dot q bar delta 2p2 dot q bar e to the minus I b dot q bar I q bar mu h bar cubed 4-point amplitude. So, okay, so, and that's why I wanted to keep the h bars, it's just to show you that there's really a h bar cubed running around in this formula. Okay, there's a question. Let me see, so there are various different factors of q. I mean, do you mean in the amplitudes or in the delta functions? Yes, yeah. So one way to think about that is if I could write that delta function as a delta prime, or, well, there'd be a delta 2p1 dot q plus q squared delta prime. That's going to, well, the amplitudes have 1 over q squared poles in them. That q squared will cancel that pole. And when you do the phase space integral, you'll get, well, you'll get one of these delta functions that Radu was talking about that forces the 2 particles to be on top of one another. So it violates the inequalities we set up. The delta function is negligible. So yeah, that's one that you can, that sort of one can understand as throwing it away for that reason. It's really a quantum effect. Another way to see that is by rewriting the Q's here in terms of these Q bars. So this one has a power of h bar relative to that. That's not unconnected to these things, but it's also essentially a quantum correction. So that's another reason why we can throw it away. If you do want to do a full computation, including all the quantum mechanical effects, you'd want to keep that. Okay, good. So excellent. So let's discuss some examples of this. So I'll evaluate this this object in a few cases, and then that'll be it for the lecture. When am I supposed to finish today, by the way?
In around 15 minutes.
In 15 minutes. Oh, okay, excellent. Yeah, that should be working. Okay, so in the last lecture, in my last lecture, I worked out expressions for a couple of 4.3 amplitudes, which you probably also saw in other contexts. So there's the 4-point amplitude in Yang-Mills theory. So there's a G squared, T1A, T2A, 4P1.P2 over Q squared. We also saw this with Radu. I'm dropping the +1 that Radu included. So there's a +1 term. If you include that +1 term in this delta P, you'll find it gives you a delta function forcing the two particles to be on top of one another. So, well, that never happens because of this, of these requirements, these Goldilocks conditions. So the delta function never fires, so we can just drop it, right? The delta function is 0. Okay, and well, yeah, very good. So we first talk about this this amplitude a little bit. So I computed this amplitude in our standard conventions. I set h bar equal to 1. So if I've kept the h bars here, I should restore the factors of h bar in this amplitude. Now, maybe it's worth doing the QED version. So let's write Yang-Mills, A4 QED, which is maybe a little bit more familiar. So then this G squared will be, let's say, the E squared. There could be two charges, Q1 and Q2 for our particles, for P1.P2 over Q squared. Okay, so now, textbooks always say that it's very straightforward to restore the factors of h bar and amplitudes, or, well, anything, right? And that's true, I guess, provided you know the dimensions of the thing you're working with, right? So we need to supply a bit of information here. So you can take it from me that the amplitudes, when you have h bar not equal to 1, you can choose conventions so that they're the same dimensions as when h bar is equal to 1, right? So in other words, normally 4-point amplitudes are dimensionless. When I insert the h bars back into the theory, this stays dimensionless. At least we can choose those conventions, right? So this is a dimensionless quantity. Okay, so now it better be that everything else is dimensionless. Now, normally, we would say, well, E squared is dimensionless, P1, P2, they're momenta, and Q squared is a momentum, so indeed it's dimensionless, right? Fantastic. So what about when h bar isn't 1? Well, P1 and P2, they're still momenta. This Q, I could still call that a Q, right? It's a momentum. So this quantity is still dimensionless. What about these things, E squared, Q1, Q2? So here is where you get to remember that alpha, the fine structure constant, is 1 over 137. That's a number. And it is E squared over 4 pi h bar C, right? I'm setting C equal to 1 because I'm not stupid enough to put C back in, and h bar. But there is a h bar that we need to restore in order to make this thing be dimensionless when h bar isn't equal to 1, right? So that's the correct expression. Now, if I include the fact, if I remember that I was talking about a q bar, and q bar is related to q by a factor of h bar, well, then I'm going to pick up another 2 factors of h bar downstairs, h bar cubed, and those h bars cancel against those. So everything makes sense, right? Unfortunately, it's not so simple that loops, which is something maybe we'll manage to talk about in the next lecture. But in this case, all the h bars just cancel in a straightforward manner, and we can forget about them for the rest of the lecture. Okay, very good. So let's do the integral. Well, when I say let's do the integral, maybe what I'll say is it is an exercise for you to do the integral. But I'll tell you what the answer is. So exercise. Yes. Okay, so an integral, we can define it like this. I d4q delta, somehow I have it as q dot u1 delta q dot u2 e to the minus I b dot. So these are really these q bars. Maybe I'll call them q bars. It doesn't really matter anymore. Q bar mu 1 over q bar squared. So this thing happens to be equal to minus 1 over 2 pi. This is related to an integral Radu, actually wrote it in the last lecture. Root gamma squared minus 1, b mu over b squared. For gamma is sensibly defined as u1 dot u2. Dot product of two particles. In the rest frame of particle 1, that is the gamma factor of particle 2. Okay, so in terms of this, so then in QED, delta P mu is, well, so we have these factors of e squared Q1, Q2. There's that minus sign, minus e squared Q1, Q2 over 2 pi. I have to worry a bit about the fact that these delta functions are written in terms of p's. So 2m1, 2m2 comes out from rewriting those delta functions like these ones. I've got the I, got the minus sign. There's a 1 over root gamma squared minus 1. So from here, there's a factor 4p1 dot p2 upstairs, which is 4m1, m2 gamma. B mu over b squared. Okay, so this factor here cancels against that factor there. The result is minus e squared q1, q2 over 2 pi. Gamma over root gamma squared minus 1. And b mu over b squared. Okay, so that's the impulse in E and M. But in the last lecture, I also worked out the amplitude and gravity from the double copy. So this allows us to work out the impulse in gravity just from the double copy. So we also found the 4-point gravity amplitude. Let me get this right. So it's minus 16 pi g. M1 squared, M2 squared, times 2 gamma squared minus 1. I've simplified it a little to get it into that form. And there's the q squared. The h bar counting, by the way, is the same as in E and M. If you wanted to put the h bars in, you can go ahead and do that. That's interesting, and it's exactly as you'd expect. So the delta p mu then comes out as, well, this minus sign cancels against that minus sign, which is good. I'll explain why in a moment. So this 16 pi, I can cancel against this thing to get a factor of 8. 8g m1 squared, m2 squared, 2 gamma squared minus 1. And downstairs, I can get that root gamma squared minus 1. And there's a b mu over b squared. Again, I have to remember that there's a 4m1, m2 downstairs because of this thing. So let's just put that in, 4m1, m2. So the net result is 2g m1, m2, 2 gamma squared minus 1 over root gamma squared minus 1, b mu over b squared. Okay, so that's the impulse in gravity, and it follows from the double copy because you can compute amplitudes, compute impulses from amplitudes. Just a quick remark. So I'm working in a mostly minus convention. B squared is a spatial displacement, so this is a negative number, which means that there is a distance b separating particle 1 from particle 2. So the impulse here is in the direction minus b. Right? So it's attractive. And that depends on that minus sign there. Now, I'm making that comment because getting the sign right, well, Radu said he got it wrong the first time he did it, so did I. And I was about to give a talk in front of an audience of relativists. And I remember thinking to myself, ooh, not going to carry a lot of, it's going to feel a bit bad if I tell them that double copy means that gravity is repulsive. So now, getting the sign right involves getting your conventions right. I tend to work in the convention. You saw it several times where I said S is 1 plus IT and the matrix elements of T are the amplitudes. That means that the Feynman diagrams are I times the amplitude. It's a different convention to the one Radu was using. So when you want to get the double copy signs right, you have to be very careful about lining up all those conventions. Okay, that's it from me. Time for questions.
So, any questions? Think about it. Comments? No? Hungry? Well, anyway, so before we go for lunch, remember, just gather here, just outside the auditorium for the group photo.